Welcome to Copilot Podcasts. Imagine trying to calculate the energy in a tiny piece of space and getting infinity as your answer. Not a really big number, actual mathematical infinity. Today, we're exploring a radical new approach to one of physics' most stubborn problems, energy divergence. We'll break down how inert primes and something called the Planck surface might eliminate infinite energies without the mathematical tricks physicists usually rely on. By the end, you'll understand why the very idea of continuous space might be wrong and how arithmetic could save physics from its infinity problem. So let's start with the elephant in the room. What exactly is energy divergence, and why should we care that physicists are getting infinity as an answer?
Energy blowup is this nightmare scenario where, according to the page content, energy densities scale as inverse powers of vanishing spatial intervals, producing non-physical infinities. Basically, when you try to calculate energy at smaller and smaller scales, the math explodes.
So it's like dividing by zero, but for energy?
That's actually a pretty good analogy. The page content explains that classical analysis allows zero-sized volumes where delta x approaches zero, which implies energy density goes to 1 over delta x to the fourth power, approaching infinity.
And this isn't just some theoretical curiosity. This actually breaks our understanding of physics?
Absolutely. According to the research, both classical and quantum field theories encounter this divergence problem. It's been plaguing physics for decades. The traditional approaches, cutoffs, renormalization, regularization, they modify the theory to remove infinities but don't eliminate their structural origin.
So we're basically putting band-aids on the problem instead of fixing it?
Exactly. And here's where this paper gets really interesting. The author proposes that divergence arises from a deeper assumption, that space, time, and spectral modes form a continuum. What if that assumption is wrong?
Wait, you're saying space and time might not be continuous? That's wild.
That's exactly what the paper suggests. Instead of a smooth continuum, we get a discrete arithmetic substrate. And the key players in this framework are something called inert primes.
Okay, I need you to break down inert primes for me. What makes a prime number inert?
According to the page content, inert primes are defined as the set G equals P in P, where P equals 3 mod 4. So these are prime numbers that leave a remainder of 3 when divided by 4. Think 3, 7, 11, 19, 23.
And these specific primes somehow solve the infinity problem.
They serve as what the paper calls the structural backbone of the arithmetic surface. The research assumes these primes have successor ordering, irreducibility, and recountability. Basically, they create a discrete framework that replaces continuous space.
This is starting to sound like we're rebuilding the universe out of prime numbers.
In a sense, yes. And here's where it gets mathematically beautiful. The paper defines an energy functional, E of t semicolon, G of n equals 1/2 times t minus a sub n squared plus alpha over 2 times t minus b sub n squared.
Okay, that's a lot of math. What does this energy functional actually do?
The beautiful thing is that this functional is strictly convex, which means it has exactly one minimum point. At equilibrium, the energy equals 0. For any other point, the energy is positive. So we've built in a natural energy minimum.
So instead of energy blowing up to infinity, it naturally settles at 0?
That's part of it. But here's where non-standard analysis comes in. The page content explains that within NSA, energy decomposes into equilibrium energy plus an infinitesimal term.
Non-standard analysis. That sounds like something from a sci-fi movie. What is it?
Non-standard analysis was developed by Abraham Robinson in the 1960s to make infinitesimals mathematically rigorous, giving calculus a foundation that Newton and Leibniz could only dream of. It lets us work with infinitely small numbers in a consistent way.
And this helps with our infinity problem how?
The paper defines physical energy using something called the standard part map. Since infinitesimals vanish under this projection, the physical energy becomes exactly 0. They call this projection the Planck surface.
So the Planck surface is like a filter that removes the problematic infinities?
More than that. The paper argues that the Planck scale isn't actually a physical length, but a structural boundary in arithmetic itself. At this boundary, infinitesimals replace divergent limits.
That's a completely different way of thinking about the Planck scale. Most people think of it as the smallest possible length.
Exactly. And here's the mathematical proof that divergence is eliminated. The paper shows that if energy diverged, you'd have physical energy approaching infinity. But since physical energy equals the standard part of infinitesimals, it must equal zero, which contradicts divergence.
So it's mathematically impossible for energy to diverge in this framework?
That's right. The page content states clearly, all physically realized energy is finite. Divergence is confined to infinitesimal structure and removed at the Planck surface.
This is fascinating, but I'm wondering about the practical implications. How does this connect to real physics?
The paper provides a dimensional audit that maps these abstract concepts to SI units. The wavelength of 29.367 meters mentioned in the paper is roughly the length of a basketball court. Imagine the universe's fundamental unit being something you could walk across.
Wait, so there's an actual physical scale associated with this arithmetic structure?
According to the appendix, yes. The inert primes g equals 3 mod 4 correspond to spatial coordinates with a characteristic wavelength of about 29.367 meters. The non-inert primes represent temporal periods of about 97.96 nanoseconds.
So we're talking about a universe where space is chunky at the scale of tens of meters, not at the Planck length?
That's what the dimensional analysis suggests. And the interaction between spatial and temporal components yields what they call the successor frequency of about 10.208 megahertz, the tuning fork of the universe.
This is getting pretty wild. But I have to ask, how does this connect to something as famous as the Riemann hypothesis?
This is where the paper gets really ambitious. It claims that the successor-generated heights exactly realize the non-trivial zeros of the Riemann zeta function on the critical line. Basically, the same arithmetic structure that eliminates divergence also solves one of math's biggest unsolved problems.
Hold on, you're telling me this approach claims to prove the Riemann hypothesis as a side effect?
The paper presents what it calls the zero realization theorem. It shows that if the zeta function evaluates to infinitesimals at successor admissible heights, then by analyticity and isolation of zeros, those heights must be exactly the zeros.
That seems almost too good to be true. One framework solving both energy divergence and the Riemann hypothesis?
The paper argues that this isn't coincidental. The same discrete arithmetic structure that prevents energy blowup also constrains where the zeta function can have zeros. It's all connected through what they call the Dirac rotation map.
And this Dirac rotation map does what exactly?
According to the paper, it maps the successor primes onto the critical line where all the zeta zeros are supposed to live. The paper even includes a visualization they call prime ballet style, showing this rotation.
Prime ballet, I love that imagery. But let's step back. What are the broader implications if this framework is correct?
Huge implications. The page content lists them. Physically realized energy is finite at the Planck surface. All Riemann zeta zeros are exactly realized. Divergence and infinite spectral accumulation are eliminated structurally. No renormalization required.
No renormalization. That would be revolutionary for physics. Renormalization has been the standard approach for decades.
Right. The paper argues that divergence isn't a property of physical reality. It's a consequence of assuming space and time are continuous when they might actually be discrete at the deepest level. If true, it would fundamentally change how we think about the universe.
This reminds me of how digital images look continuous from far away, but are actually made of discrete pixels.
That's actually a great analogy. And just like pixels prevent certain visual artifacts, the discrete arithmetic structure prevents mathematical divergences. The paper concludes that we get a universe where vacuum energy is finite, stable, and causally coherent.
But I have to ask, this is a pretty radical departure from mainstream physics. What would it take to verify or test these ideas?
That's the million-dollar question. The paper presents a mathematical framework, but experimental verification would be challenging. You'd need to detect signatures of discrete spacetime structure at scales much larger than typically considered fundamental.
And if the characteristic wavelength really is around 30 meters, that might actually be detectable with the right experiments.
Potentially, yes. The 10.208 megahertz frequency mentioned in the paper is in the radio spectrum. If the universe really has this fundamental frequency, it might show up in precision measurements of electromagnetic phenomena.
So we might be able to tune into the universe's fundamental frequency like a radio station?
In principle, maybe. Though the paper emphasizes this is about the structural foundation of reality, not necessarily something you detect directly. It's more like the underlying grid that everything else is built on.
This whole framework is pretty mind-bending. What strikes me most is how it connects pure mathematics to fundamental physics.
That's one of the most elegant aspects. The paper shows how number theory, specifically properties of prime numbers, could be the foundation of physical reality. It's like the universe is computing itself using arithmetic.
And if this is right, it means some of our most abstract mathematics might actually be describing the deepest level of reality.
Exactly. The paper suggests that what we call physical laws might emerge from pure arithmetic relationships, space indexed by inert primes, time ordered by successor transitions, energy minimized at equilibrium, and projected via non-standard analysis.
It's like reality is running on a cosmic computer program written in the language of prime numbers.
That's a beautiful way to put it. And the program is designed to avoid crashes, no infinite loops, no division by zero, no energy blowups, just stable, finite, causally coherent computation.
So when you step back from all this mathematics and theory, what we're really talking about is a completely different picture of reality. One where the deepest level isn't continuous fields or particles, but discrete arithmetic relationships.
Right. And what's remarkable is how this discrete foundation naturally prevents the infinities that have plagued physics for so long. Instead of fighting divergences with mathematical tricks, the structure itself makes them impossible.
It's like building a house with materials that can't catch fire instead of just having really good fire extinguishers.
Perfect analogy. The paper argues that we've been treating symptoms when we should have been questioning our basic assumptions about the nature of space and time themselves.
And if this framework is correct, it would mean that some of the most fundamental problems in physics, energy divergence, the nature of the Planck scale, even the Riemann hypothesis, all have the same underlying solution.
That's the grand unification this paper proposes. Not a theory of everything in the traditional sense, but a mathematical foundation that makes the problematic infinities structurally impossible while connecting pure mathematics to physical reality.
Whether this framework ultimately proves correct or not, it's a fascinating example of how radically different our picture of reality might be from what we currently assume. Sometimes the biggest breakthroughs come from questioning the most basic assumptions. And with that, thanks for joining us on Copilot Podcasts. The next time you hear about infinity problems in physics, remember, maybe the issue isn't with our mathematics, but with our assumption that reality is infinitely divisible. Sometimes the most elegant solutions come from the most unexpected places.